So yesterday we started talking about thermodynamics. Specifically, we went over the three types of systems that thermodynamics can be part of. Okay? Those are open systems, which can exchange matter and energy with their surroundings, closed systems, which can only exchange energy with their surroundings, and also isolated systems, which can exchange neither one of those things with their surroundings. They are, as the name would imply, completely isolated. Then we talked about the laws of thermodynamics. We've actually talked about them both, but we haven't named the second one as yet. Okay, we did talk about the first law of thermodynamics yesterday. The first law of thermodynamics is the law of conservation of energy. Okay, energy can't be created, it can't be destroyed. Okay, states that the total energy, including thermal energy, in a system and its surroundings remains constant. Whenever heat is added to a system, that is when thermal energy is transferred to it, it will transform into equal amounts of some other form of energy. Okay, and the same is true the other way. If the system is to lose heat, okay, that is transfer thermal energy away from itself, its energy will decrease. Okay? The energy is not destroyed, it is transferred or lost. Okay? But it can still be accounted for. All right, everybody okay with that? Okay, so there's two ways to change the energy of a system. Work and heat. Okay? I mean, in that way we could actually say there are four ways to change the energy of a system. You could add heat, do work, or have heat leave, or have the system do work. Okay? And then energy would be lost. Okay? If heat is transferred or work is done to the system, then obviously it would gain energy. All right? And that's all the first law of thermodynamics is talking about, is that basically you can always account for the energy gained and lost. Okay? All right. Now, the second law of thermodynamics is actually part of Joseph Black's experiment. You know, the guy who put the cold object in a cup of hot water, and lo and behold, the cold object got hotter. That old chestnut. Okay? That is the basis for the second law of thermodynamics. Energy always flows from the high energy object to the low energy object. It's often stated just as heat flows from hot to cold. Okay? So if we have a hotter object, it's going to transfer thermal energy to the cooler object and not the other way around. Okay? Is everybody all right with that? It kind of works like like diffusion. Okay? In diffusion, things naturally go from an area of high concentration to low concentration. Energy does the same thing. It naturally goes from an area of high energy to an area of low energy by the second law of thermodynamics. Okay? Everybody all right with that idea? Now, in biology, the opposite of diffusion would be active transport, where we can make things go the other way. The same is true for energy. If I put energy in, do extra work, I can actually make a low energy object transfer its heat or thermal energy to a hotter object. It's how your refrigerator and an air conditioner work. They are pumping heat from inside your house, which is cooler than outside your house. Okay? Naturally, it wants to go the other way, okay? But your air conditioner or your refrigerator, okay, are doing the opposite. They are pumping heat out into the hotter surroundings. Okay? That requires energy, just like active transport requires energy to move materials off the gradient. Okay? All right, now, the perfect machine cannot be achieved. How many people have heard the term perpetual motion machine? Okay, so the idea of a perpetual motion machine is a machine that is 100% efficient at converting one form of energy into another. Since it's 100% efficient, once it starts, it will never stop, because it will never lose any energy. Okay? Now, it's impossible to make one of these because no energy conversion is 100% efficient. Energy is always lost in an energy conversion. It's possible to make highly efficient machines, but not perpetual motion machines. The other problem with a perpetual motion machine is that if you never put any energy into it, what can it never do? Exactly. It can never do any work. It would be completely useless. Even if we built a perpetual motion machine, it would be nothing more than a scientific curiosity. All it would do is cycle. The moment I wanted it to do some work, it would stop. Okay? And why would it stop? Because nothing's putting energy into it. If I suddenly require it to do some work, energy will be taken from it and it'll stop. And that'll be it. Okay? So even if we could make one, it'd be completely useless. It couldn't possibly do any work. Okay? Because it would then lose energy. By definition, work is a transfer of energy. Okay? If it transferred energy away, it would lose that energy and then it would stop. Okay? Everybody all right with that? Okay, so there were some ideas on how to build a perpetual motion machine, all of which have huge and obvious flaws. Okay, so these were some of the ideas. This like spinning wheel here with the strangely shaped like pie pieces in it, okay, with these like ball bearings or marbles or whatever they are. So once you spun it, it should theoretically spin forever. Because as it spins, the ball will go over to the side and push down on this side, making it go this way. And when it gets to this point, the curve goes the other way, so the marble will return to the center, causing less resistance on that side. And then when it gets over to this side, it'll roll over and push the thing down. Okay, what's the problem with that? Well, all perpetual motion machines would require an initial amount of work to get them going. Then they should run forever after that.
There's going to be like friction in the center there.
Yeah, you could never eliminate friction from this central rotation point, from the bearing here. And every time one of these balls rolls, does it make noise? Is sound a form of energy? Then it's losing energy. Okay? All of those little things, okay, that are almost unnoticeable and we would overlook, represent losses of energy from a system. The sound of the marble rolling to the edge, that's a loss of energy. That's sound going into the surroundings. Okay? It's not an isolated system. This one I thought had promise, right? Because a magnet's kind of free. Okay? You don't have to put any work into a magnet. It just has magnetism. How will a magnet's magnetic properties last forever? They don't. No, eventually they lose their magnetic properties. I mean, it's not like over a week or over a year. It's years and years and years. Okay, but the idea here was that I guess a ball bearing, something metal, would be attracted to the magnet, and then when it got to the top, it would fall through the hole, and then it would come back down this ramp. Okay, and then it would get to here. What does it have to do? Go through a hatch. To lift the hatch, does that work? Then it's not a perfect machine. As soon as it has to do work, it loses energy. Okay? Now, the idea that the magnet would always be giving more work is kind of a way around it. There's an energy source in this machine, the magnet. Okay? The machine itself is not running forever on its own. It's using an input of magnetic energy. Okay? So it's kind of cheating it a little bit. Okay, second law of thermodynamics. Okay, it should be highlighted on your sheet. Okay, but make sure you put stars beside it or something. It's important. Okay, it describes the direction of energy flow in natural processes. Okay, the second law states that heat always flows naturally from a hot object to a cold object, but never naturally from cold object to hot object. Okay, everybody all right with that idea? Okay, so the first law and the second law are pretty important. I often put multiple choice questions on the unit exam. Here's a situation, which law of thermodynamics is governed by it, kind of a thing. Okay, and so you have to be able to tell. Okay, so Sadiq Carnot came up with this idea of the heat engine. Okay, remember we were talking, he was saying you could convert heat into mechanical energy. Okay, well this was his idea. If he had a high temperature area, okay, or object, and he had a low temperature object over here, heat or thermal energy would naturally flow from the hot object to the cold object. If he could put an engine in between those to capture that flow of energy, some of that thermal energy that was being transferred could be used to do useful work. It could turn a turbine or something along those lines. Okay? And then you'd be able to make it do useful work because he knows energy has to go this way. It's kind of like a hydroelectric dam. Okay? You have a bunch of water way up high, and you know gravity is going to pull it down, and all you need to do is put a turbine underneath to catch it as it goes, and it'll turn the turbine, and you'll generate electricity by the nature that water will fall due to gravity. Well, this is kind of the same idea, except instead of falling water, it's using heat. Okay? So if I've got a lot of heat here and a really cold place here, thermal energy is going to naturally go between them from hot to cold. If I put something in between, that's my heat engine. Okay? It's actually how a jet engine works. Okay? A jet engine has basically got a bunch of really small fan blades, okay, that turn rapidly to create thrust. Okay? So what they do in the jet engine is they have the area where the fuel is burnt. Okay? The fuel for a jet is JP5. It's essentially kerosene. It burns really, really hot. Okay? So they burn that, and then the energy naturally wants to go from the area where it's hot to where it's cold. If the plane is moving, or the fan blades are moving even the slightest amount, that can be drawn out the back. And as it goes, it produces thrust. Okay? And it can actually be shot out the back, okay, at a high rate of speed, producing a force that drives the plane forward. Okay? Everybody all right with that? Okay? It works a lot better if the plane is in motion. Jet engines are not terribly efficient when the plane is stationary. They can get it going, but they work a lot better when air is naturally trying to be rammed through them, okay, by the fact that the jet is going fast already. Okay? That just kind of adds to the force that the heat goes through with. Okay? But it's also why you have to be careful about foreign objects around jet engines. You guys all know the whole Miracle on the Hudson thing, right? If birds fly into the engine, okay, they will demolish the engine because the little blades are very fine, okay, and they're angled in a certain way so that they spin and produce thrust. If anything gets in there and wrecks any of those blades, okay, the engine no longer can produce thrust. Okay, so that's why if you've ever noticed, the next time you go to the airport, look down at the tarmac. It is immaculate. There's nothing around on the ground, and if there is, it gets picked up almost immediately, because anything gets sucked into that engine, it can damage the engine, and that's really expensive.
Well, there's a guy who his whole job at the airport is just to scare away birds with
Yep.
different bird calls and just shooting flares and stuff.
Yeah, and some places will have just almost like bear bangers. They're like shotgun shells with no shot, and they have them spaced around airports to scare birds away, keep them from entering the airport space. Some places also use that ultrasonic stuff that's supposed to keep it's supposed to work on mice, but apparently it also works on birds to an extent. It's just anything to keep birds from flying into the area where planes are always coming in and out, because obviously you don't want birds flying through jet engines. The two do not go well together. So. All right, so when heat in a heat engine flows from the high temperature area to the low temperature area, the heat can be converted into mechanical energy, which can do work. All right, so a heat engine is a device that converts heat into mechanical energy. That was Sadiq Carnot's idea. Okay? In an internal combustion engine, like you would have in your car, the fuel in the combustion chamber burns at a high temperature. Okay? So when we ignite the fuel gets hot and trapped inside the cylinder. Okay? You guys have some idea how an internal combustion engine works?
Yes.
Okay, so inside an internal combustion engine are pistons. Okay, they go up and down, okay, and that's what produces the driving force that propels the wheels. Okay, but the reason they move up and down is because when you detonate the fuel, so on top of a cylinder is something called spark. There's a picture of it. No, I don't have it. I guess I don't have it on here. Anyway, so you've got pistons that move up and down. At the top of each cylinder is a spark plug. aptly named. It just sparks. Okay? And when it sparks, it ignites the fuel. When the fuel ignites, it's actually not like a fire. It's an explosion. Because as the engine has been running, the piston has been coming up and compressing the fuel and the air. Okay? So it's basically enriched the oxygen and fuel into a very concentrated area. When the fuel is then ignited and the explosion happens, the expanding gases push the piston back down. Okay? That's what we call the power stroke of a four-stroke motor. Okay? So that piston moves down, and that's the power that drives the car forward. Okay? And then there's three other strokes that are basically just part of expanding and collecting the gases. So there's the intake phase, the compression phase, the power stroke, and the exhaust phase. Okay? So there's four strokes to one cycle of an engine, of an internal combustion engine. But it's heat being converted into mechanical energy. It makes gases expand, and that can do useful work. Okay? So this was Sadi Carnot's theoretical idea of the heat engine. And this was never built because it's completely impractical. He said, if we made a boat with a turbine in it, we could actually harness the fact that water near the surface is warmer than water in the deep parts of the ocean. So if we had, this part of the engine here with a pipe that was in the shallow water, okay, and then we've had this part here where the pipe goes all the way down to the deep part of the ocean where the water's cold, heat would want to flow from the warm water tank to the cold water tank and turn the turbine in the middle. That's great in theory. But what's the water's motivation to go through there when the hot and the cold are already in contact with each other? Nothing. Okay? There's no motivation for it. The water is already cycling naturally in the ocean. Okay? There's not really any motivation for it to do that. Plus, the temperature difference is quite low. Okay? We're talking about maybe at the surface it's like 15 degrees, and if it's, how deep can you make that second pipe? Okay? I mean, if you were at the Marianas Trench, you could make that pipe like 3 miles long or whatever. Right? Then you maybe get some difference, but it's not practical to do that. That thing would be dragging on the bottom and getting broken all the time. So it just wasn't practical to build it. It was just a theoretical exercise. Okay? But this is how heat engines work. It's also how a jet engine works. A jet engine is a turbine. Okay? You've got the hot air where the ignition of the gas is happening, and then you have the surrounding cold air. It's also why jets typically fly at high altitude. Okay? They fly at high altitude because the temperature of the air is much colder. And it's more efficient to have a heat engine when there's a big difference between the hot and the cold. All right. I don't know what happened there. Okay, so heat engines and heat pumps. So a jet engine is a heat engine. Okay? There's a hot area and a cold area. Okay, and then your air conditioner is a heat pump. So what happens with your air conditioner or a refrigerator is they kind of do active transport, which we'll get to here in just a second. Okay, so heat engines, okay, they can be mechanical heat engines where something flows and turns a turbine, or they can be thermoelectric converters. Okay, like a thermocouple basically. Okay, if there's a difference between hot and cold, so in this electrical thing here, we got 90 degrees Celsius water next to 10 degrees Celsius water, and then we've got these iron bars or whatever, or probably copper bars, running to the electric motor. So since this stuff is hotter, the particles in this part move faster than they do on this side, and so naturally there's a flow of energy through that system that would drive the motor. Okay? How long will that go for? Exactly, till the water evens out in temperature. And it'll go slower and slower and slower as that temperature differential starts to equal out. Okay? Setting it up this way makes no sense. The heat's naturally just going to do this. Right? If they're that close together, the heat's just naturally going to go right across. What does it need to go through the motor for? Okay? You probably want to have like insulated containers or something like that to make that work better. Okay? All right, a heat pump. So here's how your air conditioner or refrigerator works. So you probably noticed that there's sometimes warm air coming out from underneath your refrigerator. Okay? When it's running, anybody ever notice that? Okay. And you also probably noticed that when you open up the refrigerator, it's cold inside. True story. Okay. So the way that that happens is your refrigerator has coolant lines that run all through its walls, its top, all of that. Okay, there's these coolant coils essentially that run through it. So coolant, which is made of a special material, used to be Freon. Okay, now it's non-CFC refrigerant. Okay, so it's not as harmful to the environment. Okay, but that stuff goes through these lines, and it absorbs heat from the food inside. When it absorbs that heat, it goes from being a liquid to a gas. Okay? It rapidly changes state from liquid to gas inside the coolant lines. Okay? And it absorbs a great deal of energy in doing that. Then that now gaseous coolant goes down to the compressor. That's the thing you can hear running, okay, in the refrigerator. That's the compressor. Okay? When the gaseous or vaporous coolant gets there, the compressor does exactly what its name would imply. Puts pressure on it and forces it back into a liquid state. When it gets forced back into a liquid state, it gets hot. It releases all the energy that it absorbed when it turned into a gas. Okay? So it took energy from the food to turn it from a liquid to a gas, and then when it went back to the compressor squeezed it until it went back into a liquid state and released its energy. That's why the warm air comes out from underneath the refrigerator. Okay? It's essentially venting the heat that it picked up from the food inside. Okay? And then that just keeps going. Right? So your compressor isn't going to run all the time, but once all of the, there's a pressure change that's detected, then the compressor will run, it'll convert all that stuff back to a liquid and send it back out, it'll stop, the coolant will sit in the lines until it picks up energy and changes back to a gas, the compressor will run, okay, and so on and so on. You don't want the compressor to run all the time. It'll burn out. That's why you can't use your refrigerator as an air conditioner. Okay? Because all that's happening is the place where the refrigerator is trying to vent the air, okay, so underneath here it's venting the heat into the room. If I leave the door open, the heat just goes straight back into the refrigerator, and the refrigerator just runs constantly because now, instead of trying to cool 26 cubic feet of air inside the refrigerator, it's now trying to cool your whole house. And it was never designed to do that. That's what your air conditioner is for if you have one. Okay? But the refrigerator will just run continuously because all the heat it absorbs, it vents right back out and has to cool again. Okay? So it'll quit. It'll just burn right out. I don't know if you ever saw the episode of The Simpsons where Homer tried to use his refrigerator as an air conditioner. Okay? In his words, he said, I opened it up and noticed it was cool inside. So I put like a big blanket. I opened the door and made a tent in front of it. Well, the problem is when he made the tent in front of it, all the hot air that it was trying to vent was trapped in the tent, and it was trying to cool a bigger volume of air than it was supposed to, and it couldn't get rid of the heat, so it quit, burnt it out. Okay? So don't try that, because it will definitely wreck your fridge.
Just
and look
get in
silly.
the fridge.
What's that?
Just get inside the fridge.
Well, there's that whole problem with it's actually an airtight seal, and you might A, suffocate, or B, die of hypothermia.
Put like a straw through the door or something.
Okay. I'm not discounting that that would solve the ventilation problem, but I don't think your parents would be very happy with the hole in the refrigerator.
Just put some, just get some inside of that.
Just put some more JP wool or something.
Yeah, no one will see that.
No.
No, it'll look just like new again.
Just
Okay, does everyone kind of follow how that works? Okay, the same is true for your air conditioner. How many people have an air conditioner? You ever go outside and look at it? Okay, it's like there's a kind of a big tower in the middle of it, and there's a whole bunch of coolant lines that kind of run around that. Okay, they radiate the heat. When it's running, if you go out there, you can feel the heat coming off of it. Okay, it's venting the heat from inside your house, outside your house. It's also why it takes a lot of energy. Your refrigerator and your air conditioner are the two biggest electrical draws in your house. Because they're trying to go against the laws of thermodynamics. They're essentially active transport for thermal energy. All right, I would like you guys to answer those questions right there, please. Okay, I'll give you about 10 minutes or so to do that, maybe 15 minutes, and then we'll go through them together. Okay, so for question number 2, state the first law of thermodynamics. So basically, in your own words, energy cannot be created and it cannot be destroyed. That's the first law of thermodynamics. Okay, or the energy of a system, okay, can only be changed by adding work, okay, or having it do work, or something along those lines. Okay, what's the distinction between work and heat? They are both transfers of energy. The distinction is
One's a transfer of mechanical energy, the other is thermal energy.
right. Work is a transfer of mechanical energy, and heat is a transfer of thermal energy. That is the distinction. What type of energy they transfer. Okay, identify whether each of the following is best explained by the first or second law of thermodynamics. A bouncing ball eventually comes to rest on the floor. Which law? Okay, the first law says energy can't be created or it can't be destroyed. The second law says energy flows out of a high energy system into the surroundings. Which one? It's the second law. Okay? If this was the first law, it would say a bouncing ball bounces forever. Okay? It can't bounce forever. It's losing energy to its surroundings because of the second law. It's higher energy than its surroundings. Okay, a metal spoon eventually becomes hot when placed in a pot of boiling water. Second law, energy flows from hot to cold. Okay, energy cannot be created or destroyed. I think we just wrote that a minute ago. First law. Yeah, okay. Number 7, state the second law of thermodynamics. Energy always flows from a high energy object to a lower energy object or lower energy surroundings. Okay. Number 9, this one requires a bit of thinking. So water is observed to condense on the outside of a cold glass. Which way is the energy flowing?
It's not like going in.
It is. The energy is going into the glass. That is in fact why the water condenses on the glass. Water vapor in the air is high energy. The glass is cold. It's low energy. It's so cold that the water vapor in the air turns back into a liquid when it comes into contact with it. In order to evaporate 1 gram, that's 1 milliliter of water, is going to require 2,260 joules worth of energy. That amount of energy is also given off when 1 milliliter of water vapor condenses back into a liquid. So when water condenses onto the side of a cold glass, a great deal of energy is flowing into the glass from the surroundings. Okay, everybody all right with that? Okay. It's actually how sweat works. Okay, when we sweat and the sweat evaporates, we feel cooler. Because for every milliliter of sweat that evaporates from our bodies, we get to get rid of 2,260 joules of heat. Okay, so that's why if you get really sweaty and then you go outside when it's super cold, you can get hypothermia really fast because that water continues to evaporate even if it's cold outside. Okay, and so you're losing energy and you get chilled. Yes. Okay, number 10. Which law of thermodynamics best describes the following statements? You can't get something for nothing. First law. Okay, you can't even get close to getting something for nothing. Still first, yeah, but kind of also the second. You can't get close to getting something for nothing because energy is always flowing away. Okay? Kind of like why you can't have a perpetual motion machine. A rock will never suddenly jump into the air. First, yeah, okay. It can't, that would mean it created energy. If it's on the ground, it's not going to jump into the air. All right. Questions on any of those? So that's kind of the start to the physics unit. Okay. This stuff isn't really, it's just kind of additional. It kind of helps to explain some of the stuff that we've gone over. It's not something I'm going to test. Okay, but it kind of can help you understand the stuff I'm going to test a little bit better. Okay, so we didn't understand thermodynamics all that well or completely before we started trying to use them. Okay, technology often goes ahead of understanding. We have a need, we have to meet that need, we build technology to meet that need, and sometimes we don't even fully understand how that thing works. We're just able to do it, okay? And a lot of that has to do with how we kind of made engines early on, how the development of engines and other types of work-aiding technology came along, okay? One of the simplest and like kind of earliest like engines or pumps was the Archimedes Screw. And it's just like it's a big auger, basically, a big screw, okay? And you'd spin it really fast, and because of the polar nature of water, you could actually get water to move up the corkscrew, okay, and actually come out the other end of the pipe, okay? So you would just turn it really fast. Big limitations to the Archimedes screw, it worked great as long as it was less than 2 meters long. Okay? After that, you couldn't spin it fast enough before the polar nature of water wasn't enough to keep it on the screw, and it would just run back down. Okay? You just couldn't go fast enough, right, in order to make that work. Right? The Persian Wheel, same thing. It's just got cups on it, okay? And the cups would take it from, you know, like a body of water, a pool or whatever, and get it onto like kind of a ramp and make it kind of go down. And you could get it to do that because you'd lift it up to this height, drop it, it would gain energy, and be able to go up a little bit. Okay? What else we got here? All right. Getting pumps that work in more than one direction is pretty important. We call that a reciprocating pump, okay? And it involves the use of valves. So for this recirculating pump, you have your piston that creates the pressure, okay? When the piston moves back, it sucks this valve, the top valve, down, which seals the upward chamber. But that suction lifts the bottom valve. Okay, drawing water into the pumping chamber. Okay, the opposite is true when the piston starts to go back in the other direction. When the piston starts to move this way, the pressure closes the bottom valve and pushes open the top valve, allowing the water to be pumped no matter which direction the piston is moving. Okay, it was kind of a big kind of leap forward in like engine and pumping technology to come up with this reciprocating pump idea. Okay, now people understood and wanted to make mechanical energy, but there weren't a lot of ways to get it other than burning stuff. And burning stuff doesn't make mechanical energy, it makes thermal energy. Okay, so there had to be a way to turn that thermal energy into mechanical energy. Okay, that's where the piston, the cylinder, and the engine come into play. Right? One of the first steam engines, okay, was this, okay, Papin's steam engine. It didn't reciprocate. So you would have a big coal fire, and you would have this drum that had a piston in it that was full of water, okay, and as you heated the water, okay, the piston would be down here. When the water was all liquid, the piston would be down here. But as the water heated up and boiled and turned into steam, steam takes up more space than liquid water, and it would exert pressure, turning heat into mechanical energy that would lift the piston into this position, and whatever the piston was attached to would move. Well, that's great. How many times do you get that to work? Once. Once the piston gets to the top, you have to cool the whole thing down again in order to get the piston to come back down. Is that very efficient? No, especially since cooling the whole thing down meant throwing water on the side of this thing, which, you know, would inconveniently put the fire out, which then you had to start the fire again. So this was not a thing that works like an engine today, which can, you know, our internal combustion engines can rev at several thousand revolutions per minute. This was like one revolution every hour, if you were lucky. It just wasn't very efficient that way. But it showed that you could turn thermal energy into mechanical energy. So in that way, it was a step forward. Okay. Now, people thought, all right, that's too slow. So there's got to be a better way to do it than that. Okay. So they came up with the gunpowder engine. I don't think we have a, no, we do have, okay. So the gunpowder engine, okay, was never actually built because, well, it would have been very, very dangerous. It's essentially a cannon, except the ball isn't allowed to be fired. The ball is a piston. So you put all this gunpowder inside and spark it, and boom, the gunpowder explodes, which creates rapidly expanding gas, which would move the piston and do a lot of work. The problem is creating a container that can continually withstand the explosion and not blow up itself. Nobody wants to be around something like that, so it never got developed. But the idea was still valid in that rapidly expanding gases can be harnessed to do mechanical work. Right? Then engines got better. We got higher quality steam engines. Okay, we got reciprocating steam engines. Okay, built by people like Newcomen and people like that. Okay, that became more and more efficient. The problem with all of these engines is that the combustion is external. They all use steam. So inside is the water. The water heats up, steam expands, pushes on the piston. But the fire is outside. Okay? So that meant having much bigger engines. Okay? Steam engines had to be very, very big, and they were really hot. And they required lots and lots of coal. So during the Industrial Revolution, when all of this was going on, okay, there was coal being burned everywhere, and then they'd get soot and black smoke, because they didn't have the technology we have today to harness all the particulates and reduce all that kind of greenhouse gas and smog gases and things like that. So pollution was just wild, okay, during that time because of all the coal being used to do all of this. So people were looking for ways to make the engine smaller, because they wanted to be able to use it for more than like factories. They wanted to use it for transport, like trains, cars, which weren't around yet. Okay, people were thinking, wouldn't it be great if we had an engine that could move, could make an automobile, okay, something that could power itself and move, automobile. Okay, that's where the name comes from. Okay, it can move itself. So people were trying to shrink this. They were trying to minimize or make this technology smaller and more efficient. Okay, Watt's engine was even better. Okay, still steam engine, still requiring all of that. Okay, but the internal combustion engine is the thing that solved this problem. So this is the diagram I was looking for a few minutes ago. Okay, in an internal combustion engine, the combustion is, as it would imply, inside the engine, not outside. Okay, so the heat is actually generated internally. So when you have a 4-stroke engine, okay, you've got what we call the intake phase. So let's look at the parts first. Okay, in here, this part here, this is the crankshaft. This is the part that's connected to the drivetrain of your car and actually turns your wheels. Okay, then there's your connecting rod, that's this thing here, okay, and then there's your piston, and then this whole thing here is the cylinder. Okay, and up here are your intake, this is the intake valve, and this is the exhaust valve. Okay, that's a simple engine. If we're looking at like a more complex twin cam type of engine like we would have now, there would actually be 4 valves per cylinder. Some engines even make 6. Okay, and they have different valves. If they have many valves, they have different valves for different RPMs, for different rates at which the engine is moving. Right? So in a simple engine, we would have 1 intake and 1 exhaust valve. So during the first part of the cycle, okay, we have what's called the intake phase. Okay, so the piston is actually moving in a downwards direction. Okay, and it's called intake because the intake valve opens and a fuel-air mixture is pulled in to the cylinder. Okay, so there's a vacuum created by the cylinder or the piston moving down, and it sucks in the air-fuel mixture. Right? Once the piston gets to the bottom, like you see here in the second picture, right, the valve closes. And now that both valves are closed, the piston can start moving back up again. When it moves back up, it compresses the gases. Okay, so this is the compression phase. Okay, this one right here. This piston is moving up, the gases can't escape, so they get compressed. At the top of that stroke, okay, is when the spark plug ignites. Okay, so just a little electric spark happens and it ignites the fuel. Okay, this part here is what we call expansion or the power stroke. Okay, so that's the part where the expanding gases force the piston down. Okay, turning the crankshaft, okay, and driving power to the wheels. And then in the next stroke, the piston is moving back up again, but now the exhaust valve is open and all the spent gases are being pushed out and into the exhaust system. Okay, that's very basically how an internal combustion engine works. Okay, now we've made huge advances in the internal combustion engine in the last 30 years. They're far more efficient than they ever have been. But they still try to turn heat into mechanical energy. That is what they do. How much of that heat actually drives the car forward, do you suppose? Way less than half. It's less than 20%. Less than 20% of the energy and fuel in a relatively efficient car is actually converted to mechanical energy. So much heat is generated by the explosion of gasoline that most of your car's energy is used to keep itself from melting down. 30% of the energy in your fuel drives the cooling system so that your car doesn't overheat and seize. Okay? It's pretty important, okay, to keep it cool. So there's stuff running to prevent the heat, but the heat is needed to make the power, okay, and all of that. So yes, like when we look at it from strictly an efficiency point of view, it doesn't seem very good. But when you look at it from it's transportable, it's miniaturized, okay, it's not burning coal to heat water to move a piston, it's quite efficient. It was a huge leap forward. And like I said, we're getting better at making this a more and more efficient process. So electric cars obviously don't have any of this. They've just got a big battery with with several probably electric motors. Okay, so electric motors are about 95% efficient. They generate very little heat, some, but not a lot. Okay, because there's very little internal friction in an electric motor. So an electric motor works. You've got like a whole bunch of magnets, right? And they change which ones are kind of pulling and which ones are pushing in order to spin the motor. But since there's very little contact with anything, there's virtually no heat generated, and that's what makes them so efficient, okay, is that they convert 95% of the electricity that goes to them into mechanical energy. Okay, so getting an electric car is going to help the environment in that it is more efficient than a gasoline-powered engine. In terms of reducing your carbon footprint, it may not do as much as you would like. Okay, not a lot of people get an electric car for all the right reasons. They want to do their part to, help the environment and reduce their carbon footprint, and they do that to an extent because electrical cars are more efficient than gas cars. The problem is, where do we get our electricity from? Burning coal. So you're kind of just transferring the burning to somebody else. It's not really stopping it. You still need enough energy to get your car from home to work and back again. So if you're plugging in here, well, most of our electrical grid is powered by fossil fuels. We can look at the wind plant down in Pincher Creek, which last year underwent a massive expansion. There are literally twice as many wind turbines down at the Pincher Creek wind farm than there were a year ago. Okay, we're expanding that. It's great, and it's going to reduce our carbon footprint. But still, the vast majority of our electrical grid is powered by the burning of fossil fuels. So plugging in more electric cars just means we're burning more fossil fuels. Okay? It's certainly still going to help the environment in that the coal plants are probably better at catching all of the emissions than your car, and your electrical car is going to use less energy than your internal combustion car. So in that way, you are doing your part. It's probably just not as much as you think you're doing. Okay.
Are diesel engines more efficient than gas engines?
They are, in general. Problem with diesel engines is what they produce is worse. I mean, there's a reason why there's nicknames for all of the diesel engines. Like, the Chevy's Duramax is often called the Dirty Max, okay? Because it puts out a lot of sulfur. Have you seen any of those guys that have the chipped ones? Okay? And they hit the gas, and this cloud of black envelops everyone. Okay? That's not very good. So yes, a diesel engine is more efficient, but it also puts out a lot more emissions. And now, in order to curb that, there's a cycler that the emissions have to go through in most diesel engines, and it's you have to keep putting in the fuel conditioner. It's urea actually, and the urea absorbs it's sulfur. It's one of the pollutants. I can't remember exactly which one, but it helps to absorb that, and it collects, and then basically when you change your catalytic converter or whatever it is, then all of that absorbed stuff is taken away. I don't know what they do with it, but it does reduce how much of it is put into the air. And so yeah, you have to have, people will cut those off. Okay, it's like one of the first mods that somebody trying to get more power out of their diesel engine will make is to cut all of that off and replace the sensor or change the chip to trick it into thinking it's still there. And those are the ones that put out that big cloud black smoke. Okay, that's why we call them red chipped, because they've replaced the pollution chip that tells them, oh, you're doing a great job. Kind of like what Volkswagen got in trouble for.
Yeah.
Okay, did you guys hear about that? It's called Dieselgate. Okay, Volkswagen had reprogrammed the computers in their diesel engines so that when they hooked them up to do an emissions test, the computer would lie to the computer doing the test. They would say, oh, we're doing wonderfully, we're converting this many things, but it wasn't. And they were actually way worse than they were supposed to be. And Volkswagen got sued massively. And they actually had to recall a ton of their own vehicles and redo the whole emission system at their own cost. Cost them billions of dollars. So, don't cheat. You'll get caught. Cheaters never win.
It's fine, Volkswagen's rich.
Yeah, but that was a big one. Like, I wouldn't have wanted to have stock in Volkswagen when that happened, because that was a big one. It was billions and billions of dollars. Okay, so that kind of, it's just an example of how heat or thermal energy can be converted into mechanical energy. It's kind of a big part of the unit. That whole heat and mechanical energy relationship is a big part of all the stuff that we're going to talk about. Okay, yeah, so the idea here was you got this internal combustion engine. The first one was actually built, I think, in Italy, okay, and it made 1 horsepower, which, for people at the time was like, sweet, 1 less horse to feed. Okay, and that is why we rate engines in horsepower to this day. Okay, when the engine was first made, it was made to replace horses. So I don't know what they did with the horses. I don't want to think about what they did to the horses, but okay, they replaced horses, okay, and so horsepower was born. When a farmer went to the tractor, to the John Deere dealership, he's like, okay, I need a tractor. My horses are old and they don't pull very good anymore. How many horses am I going to replace with this? Well, this is a 25 horsepower tractor. Well, I only have 8 horses. That seems like a good deal. Okay, I can replace all of them plus 13 more. Okay, so there's that. So I don't know what I said there, what numbers I picked, but okay, that's what we're looking at. Okay, is that horsepower was given that name because it told us how many horses it could replace. If you actually go car shopping now, lots of cars, their rating is in watts, which is the metric unit for power. Okay, I remember looking at one of the stickers and I was like, is that good? Is that a good number? Like, I mean, I know what watts are, I know what kilowatts are, but when it comes to how powerful a car is, I don't know, like, my blender is 1200 watts. I'm trying to make a comparison here. How many horses are under the hood of this beast? Okay, right? But like my truck, it's like 400. It's awesome. It's very concentrated. 400 horses fit in that little space. Okay, great. Okay, but when you're looking at like more efficient vehicles, a Tesla is not rated in horsepower. I mean, you can do the conversion. You can convert watts to horsepower, but it's rated in watts because it's electric. Okay? And incidentally, are Teslas fast?
Yes.
They're wickedly
Because
fast.
they have a lot of torque.
Yeah, and they don't waste any of it. With an internal combustion engine, a lot of the torque that's produced, if you look at like a big muscle car, like something like a big supercharger, tons of horsepower, okay, a lot of the energy is wasted because the tires will spin. Okay? They're not driving the car forward if they're spinning. Because a Tesla's all electric and all computerized, if any wheel starts to spin, automatically that power is diverted away from that wheel to a wheel that's gripping. Okay? And so the tires, the wheels never spin in a Tesla. So it generates all the torque, goes straight to the road and propels the car forward. It was like, I watched this drag race between, on YouTube, between a Dodge Challenger Hellcat, 710 horsepower, supercharged, like just like testosterone, chest thumping beast, okay? The Tesla. And the Tesla scorched it every time. Okay? It just wasted so much energy. Granted, it looked way cooler losing, than the Tesla did. Like Tesla just took off and went, okay? But it didn't do anything like really cool other than go fast, okay? Meanwhile, you're watching the tires smoke and envelop everything in sight, okay? From the other one, and you hear the sound that's just kind of pleasant, okay? But yeah, it's not efficient. An electric engine is more efficient. There's no way around it. Like, the only drawback for electric cars is what?
Expensive.
Okay, I would agree. Like, a year ago, I would have totally agreed with you, except you can plug in an electric car for free.
Well, I was doing I tried to like figure out like how much a Tesla would cost. I guess that's like more of the other features of like the self-driving stuff. It's like $10,000 just for that.
At least, yeah, yeah, when you're looking at all of that. But then, if you plan it right, like one of our IT guys, he drives a Tesla. Outside of board office, there are 3 electric car charging stations. So he gets free gas. He drives to work and plugs in. He doesn't pay for that. The city, the town of Okotoks, powers that charger. So yes, you're gonna lay out more money initially for your Tesla, but I think it's gotta pay off pretty quickly when you're not paying to charge it. Because if you charge it at home, your power bill goes up. Not by as much as the amount of dollars of gas you would have put in an internal combustion engine, but still goes up. You know, your energy is energy, right? But if you plug it in at work where you don't pay for it, you get free gas. So maybe it pays for itself. Like I'm starting to think the reason we're seeing so many is because people have figured that out. There are a lot more charging stations
I
out there.
think also it's their inability, like they're not that good in Canada because the environment.
Yes, in cold, lithium-ion batteries are far less efficient, and that's what they run on. So yes, in the winter, your range is going to be decreased. But in a place like Okotoks, a Tesla is a great idea. You never have, like if you're just driving into Calgary, like most people do from Okotoks, it's a great way to save money on fuel, help the environment, okay? Do all the things that buying an electric car is supposed to do. And because you live in Okotoks and there's a million free charging stations, you get free gas. So as long as, someone else isn't parked there.
But if you go to Louise, then you're like, if I get caught in a snowstorm and I have the heated seats on and the heat, then you're like, I might not make it back home.
Yes. An electric car is not a road trip vehicle.
Yes.
Unless you can plan your road trip around where a fast charge station is. But a fast charge is still not like pulling up to the pump and going and then getting back on the road. Okay? That takes like 5, maybe 10 minutes. Fast charge is what, 40? Something like that. You'd have to sit down and have lunch. I mean, you gotta do that anyway, but you have to plan your trip a little more around where you can plug it in. So yeah, you go to Lake Louise in the wintertime, maybe you've got enough power to get back. For me, that's stressful. I can't deal with it. I just put gas in. Although, when gas is $2 a liter, it starts to think about it. So hybrid cars, good question. So a hybrid car has both. Okay, a hybrid car, the advantage of a hybrid car is that you're using a smaller gas engine combined with electric motors. Okay, so like I'll give you an example. We currently have on order a Toyota Highlander hybrid. And so instead of having the big 3.5 liter V6 that our current one has, it now has a smaller 4-cylinder engine. And both back wheels have electric motors. So the gas engine only powers the front wheels. The electric motors power the back wheels. It can go in full electric mode in certain situations and just run the back wheels and power the car. But a hybrid works by having the smaller engine help the electric engine, or the electric engines help the smaller gas engine. So if I'm accelerating stop and go traffic, hybrids are awesome because whenever you hit the gas and you need the extra power, you're using a smaller engine and the electric motors will kick in and assist. And it feels just like you're using a bigger motor, but you're using less fuel because you're actually using a smaller motor. Anytime the internal combustion engine is on, it's also charging the electric batteries. So it's hybrid in that you don't just plug it in. The gas engine is what charges the battery. Unless it's a plug-in hybrid, then you can plug it in as well. But most hybrids are not plug-in, so the gas engine charges the batteries, and whenever the gas engine needs help, the electric motors kick in and assist. So that's how it becomes more efficient. So a hybrid vehicle is much more suited to stop and go traffic than it is to a long highway trip. Okay? You'll get more savings and get more environmental benefit out of using it in stop and go traffic than to just get on the highway and drive 1,000 kilometers a day. It's still gonna be more efficient that way than a gas engine, but not, the benefit isn't as great. So that's kind of how it works, if that makes sense.
If they're so beneficial, why aren't we seeing them so common?
They're becoming more and more common. Some people just don't like it. Like, I was pretty resistant to getting one, until, we kind of sat down and looked at the economics of it and went, okay, this thing will get 6.7 liters per 100 kilometers. Our current Highlander, on a really good day with the wind behind us going downhill, will get about 10 and a half. My truck will get about 10 and a half on the highway. So it's a pretty substantial savings, and we can get that in town, where the Highlander and my truck are looking more like 13, 14 liters per 100 kilometers. It still gets 6.7. So it's less pollution, it's less gas, and at $1.57 a liter, that's significant. So more and more people are going that way. In Alberta, we see less because of the nature of Alberta. They still have lithium-ion batteries, which are less reliable in winter. And Alberta is the pickup truck capital of the world. More pickup trucks per capita in Alberta than anywhere else because of the nature of work in Alberta. Lots of people are in oil and gas where they need a truck, okay? Or they have to tow a trailer, they would need a truck. Hybrid trucks are only now kind of becoming a thing. They still have the limitations on, okay, we need power for this. Can we get it from an electric motor? Can we get it from a hybrid system? Okay, like Ford actually now has the Lightning, the F-150 Lightning. You can get an all-electric F-150. Okay, I don't know how good that is. I haven't read the reviews yet for towing and payload and stuff like that. Maybe it's good enough. Again, range is always going to be your problem. If you have to draw on those electric motors while towing or carrying a lot of load, they're not going to last as long.
Does it have to work better than an electric car that can hold?
Yes, in winter, the problems with the electrical are less because you have the internal combustion engine as well.
What about like the disposal of electric batteries?
Well, that's the other environmental thing that they don't tell you, they don't speak of much. Lithium-ion batteries have to be disposed of somewhere, and there's a lot of really toxic materials in them. But when you look at how many tons of CO2 you don't put in the atmosphere versus the 400 pounds worth of battery that has to go somewhere, there's a lot of regulations around those disposals. It's where does the scale
I'm sure
go?
like most of them can be like only 5 or 10% used.
It's possible.
It's like low though.
We're gonna have a lithium problem if we don't learn how to reuse it or.
See in like 5 years when some of these like 2016 metals start to like go down in the range, and then we're like, oh, where do we put all these batteries?
Well, and where do we get it from? If you've ever seen what a lithium mine looks like, okay, like a lithium mine is a gigantic hole in the earth. Okay, it makes the tar sands look like beautiful flowers. Okay, so yeah, it's where does it? Like, pick your poison. You gotta get energy somehow. The law of conservation of energy says so. Okay, guys, for your test tomorrow.